Welcome back in our series of tutorials about running the local fine-tuned LLM in our Raspberry Pi brained robot as Mars rover. In previous video we created dataset for fine-tuning our model. In that video we'll realize the fine-tuning, we'll write all the script and run that. And in the next one I will show you how to run the fine-tuned model in our Raspberry Pi and how to set up remote monitoring and debugging it. But for now, let's start with fine-tuning. So let's take a look now for my script for fine-tuning the LLM. First of all, here we uploading our train and evaluation dataset, and next defining our model ID. I tried 3 different models: Zephyr, Mistral and Dolphin, and in my opinion for that task Zephyr provided the best output. If you wonder how to find exact name of the model, you can just go to Hugging Face and search for your model. For example, Zephyr. And you have here the company name and model name for that. Just copy that and paste here. Next, we configure in weights and biases, and this is platform that helps us visualize our training progress. Basically, that's not really needed, but it could be really useful. Weights and biases looking like that, and here we can find our history runs. I'm defining here model ID into one config just to know which model I have trained in every particular run. Next, we define bits and bytes config, and that is needed for quantizing our model. First of all, we taken our model from Hugging Face, and after that we need to quantize it to 4-bit version. As I explained it in previous video, quantization helps you to reduce size of the model without bigger reduce of model performance. So what exactly mean here every line I will not explain you, because I am, to be honest, didn't really know it also. But well, in the old tutorials that lines are exactly the same, so I think it should work at least not bad. Next, we apply our quantization to our model. After that, we need to set up tokenizer. Tokenizer converts our words written in the human language to the lists of numbers readable for machines, for LLMs. As you maybe know, LLMs basically work in that way that predicting every next number in the sequence of numbers, and that numbers just mirror the real words. So tokenizer needed to convert words to numbers and convert back numbers to words when our response generated. What about some particular settings of our tokenizer? Model ID to specify tokenizer, because different models can have different tokenizers. We specify it. That two settings at beginning of string token and at end of string token set to true means that tokenizer automatically, when converting our words to numbers, will add beginning of string and end of string token, and that tokens just signalize to our LLM when our text should begin and end. Basically, beginning of string token in case of the Zephyr model and many other models is just S letter in such brackets. After that we have our prompt, the response, something else. And after that we have end of string token that looks like /s in brackets. So in our case, we don't need to write it manually, we can just set up tokenizer to automatically put the tokens into the text, basically into the numbers, when we tokenizing our text. There are some settings about padding of our tokenizer, and padding, if I understand that good, is just a way tokenizer completes our prompt, our response, to maximum number of signs in it. So basically, when we don't overflow context with our prompt, it will complete it with end of string tokens from right side under the end of the context window. Okay, so maybe I will show you how does tokenizer work to make it understandable for you, because in my experience it was, well, not so obvious, and that provided me a lot of complications, lack of understanding how does it work when I tried to write that fine-tuning script. So I prepared some simple test file, and well, we have here our tokenizer, and we're asking him to tokenize some string. Maybe let's make it JSON to be more closer to our examples. Okay, let's run that file, let's tokenize it, and let's see how does it look. And we can see that our tokenized string is the list of numbers here, where that numbers is all different tokens. That means different words or signs inside of that text. And by the way, you can see that 1 at the beginning is the number of the beginning of string token, and 2 at the end is also number of end of string token. If you decode it back, you will be able to see it. And you can see after decoding our numbers back using the same tokenizer, we can have our text with beginning and end of string tokens. So now I hope you understand how does tokenizer work. If still have some questions, please ask in the commentaries. Next we configuring so-called theft or LoRa. LoRa is the way of fine-tune our models. Basically it's about changing some weights of the model, and it's not changing all the weights but only some smaller percent of the all weights, some 1-2%, something like that. And I will also not explain you what does mean every of the parameters. I'm not feel to be expert enough, but also in every tutorial that lines, that numbers are exactly the same, so I think it should work. In that lines we just applying our LoRa config to our model, preparing it for training. Next we have our prompt formatting functions. What is prompt formatting? Well, to our model understand our input data, we need to provide appropriate way of formatting. So let's open, for example, Hugging Face, and okay, here you can see way of format prompt for that model. We have first of all system provided that way. After that we need to provide some system message. After that we provide an user message and our input text, input data. And by the way, in my opinion, in our case, we don't need at all the system message because it all the time same. We just teach our model how to generate good response based only on the user input message, as it is the single variable here. We need to provide it that way, user and our input, after that assistant, and after that it will generate his text. And basically this is our response. So in such function, for all the examples, we taken our input text, and our input text is just that. Front something, right something, container full, base at rear, and this is our input text, which we provided here after the user prompt, so here, and our output text or response, which as you can guess is that the JSON that we learning him to output should be after the such assistant message. And basically that way, with that function, prompts formatting, basically in all the tutorials I seen. The problem with such approach is that different models have different ways of formatting. So basically, if we can see, for example, for Mistral, this have another way of format. Instead of system user assistant, it has inst and /inst strings around user instruction. If you can see for the Dolphin model, it has I'm start system, I'm end, I'm start user, I'm end, I'm start assistant, and so on. So basically that formatting templates is totally different. So for every different model, you need to create different function. For example, for Mistral you have that insts, for Dolphin you have that I'm starts, I'm ends, and yes, but that's why all the tutorials doing, and I was also doing that way at the beginning, but after that I found something much more interesting. Basically, tokenizer provides us apply chat template function, which allow us to provide our message in just normal template, in normal JSON that we provide a message, for example, for GPT-4 with role, user assistant or system, and content of our texts. And tokenizer automatically, based on the model we are using, find appropriate tags it needs to be passed before that input text and so on, and prepare prompt automatically, and we don't need to worry about finding appropriate separators like that. So maybe I will visualize you how does it work. So we have, let's say, the chat template. And let's see if our tokenizer will be able to automatically apply that separators on the pen of our model. And you can see that we have our separation applied for the Zephyr model, so user and assistant, exactly like you've seen here. In our case, as I said, in my opinion, we don't need any system field, so there's no system here. But if you want, you can add also some system message among that message. And also we can try to do that with some another model, let's say Dolphin. We can see that it provided some Dolphin separators. Not sure why it's inst, because it's more like for Mistral than for Dolphin. If we try it for Mistral model, let's see what will happen. Oh, and we have our Mistral type formatted with that inst types. So we can provide here any model and we will have appropriate separators automatically. Next, let's define our training arguments. First of all, let's provide our maximum sequence length, or just our length of context window, which is in my case is just 256 tokens, which is, as you probably can guess, is not very much. For example, in GPT-4 we have 8000 tokens, in new GPT-4 Turbo we have 128,000 tokens, and here we have only 256 tokens, which is could be seems not much, but in my case it's totally enough, and in my opinion is the most case we don't really need some big giant token windows. Basically, for shorter windows, we need to have less RAM for training. It's very RAM effective to have that shorter windows. So, well, just see at your data, just find the longest example. Let's say that. It seems to be the longest one. Let's copy it. Next, let's calculate tokens inside it, and what we can do, basically we can use the tokenizer function to write special Python code to calculate the tokens, or basically estimate the tokens. But simplest way we can do is just use tokenizer from OpenAI, copy our text here. Yes, we have some numbers of tokens here, and my warning that that number is not exact number of tokens we have in our text, because for different tokenizer it could be different, but more or less we have that number. So as you can see, in my case, for the longest example, the number of tokens is more than 2 times lower than length of my context window. So basically, I think I can do it even smaller if I really would. And next we have our training arguments. First of them is output directory where our checkpoints of training will be saved. And next is max number of steps of our training. So our training going in steps, and step in our case is just number of examples from our dataset trained at once, which is 4 for our case. So during all our training, we will run over 175 times 4 examples. The bigger number of steps we provide here, the longest training we will have. Next, we provide warm-up steps. To be honest, I'm not really sure about that parameter, what it will mean, why do we have that value. But I think there's some steps before real starting our training to warm up model, something like that. Next we have login steps. So there's nothing interesting, just how often we will have the login of parameters inside of our prompt printed every 10 steps. A save strategy epoch, so after every epoch our model checkpoint will save. And what is epoch? Basically, epoch is the one pass over all the training examples. So in our case, when we have 100 examples, and for every step we have processed 4 examples, our epoch will be 100 divided by 4 is 25 examples. So after every epoch, our checkpoint will save. After that, we also provide an evaluation strategy, which is steps, and we can choose here steps or epoch. In our case, we have evaluation after every 10 steps, but we can also pass here epoch, and we can have evaluation, for example, after every epoch. After that, we're setting up our learning rate, and this is the one of the most important parameters we have here. Basically, the smaller learning rate we will set up, the longer our training will take, but also it will allow us to make the training better, basically to find out the better local minimum for our model. So like I prefer to wait for a while and set up it smaller but have better results. What is BF16 I don't know, but it should be true. Learning rate scheduler type is constant, means that we have constant learning rate through all our training. It's simple strategy, but if you want to have something more advanced, you can set up learning rate to be changeable during the training. So for example, have this learning rate for first 100 of steps, for second 100 of steps can have 2 times smaller learning rate, and for third 100 of steps you can have even smaller learning rate. Basically, the further your training is going, the more precision on learning rate you need to have. Changing the scheduler type to not constant but lowering learning rate could be sometimes beneficial, but in our case I don't want to overcomplicate it, and constant learning rate will be totally enough. So that we're setting up with report to 1, which means that during our training, our progress of training will be sent to weights and biases. And finally, we're setting up our trainer, which is SFT trainer from Hugging Face, providing here our model, our LoRa config, our max sequence length, or that context window I was talking about, providing our tokenizer, providing formatting function for a prompt, so that function automatically convert our prompt to appropriate format, providing our training arguments from here, and providing our training and evaluation data sets. After that, we just running our training. Now we can run our training. To do this, we need to have a GPU with, I think, 8 GB of RAM should be fine, should be enough for such small context window as 256 tokens, but obviously the more the better. If you have GPU on your own PC which will work, it will totally fine, you can try it to run locally. I'm working now on my laptop, so I need to use some cloud providers. There's really a bunch of them. You can find some GPU on internet, rented for hours for training LLMs, for running LLMs. There are really many of that last time. I'm used Brave Dev for my purpose, and here you need to log in here, add your card, create new instance with, I think that T4 GPU, the cheapest one, should be totally enough with 60 gigabytes of RAM, and you just click in here, okay, deploy and deploy it. And they have here instance, and I will start it now. Let's wait a second. They have couple of bugs here. Sometimes they write that unable to start instance, but it's basically starting. Okay, it started, so I need to host notebook with that instance locally. Basically, if you have Linux or Mac, you can just install their application on your machine. Or in my case, when I'm using Windows, you can install it on VSL. And after it installed, you can just open the terminal on the shell or open that in Notebook. I will open it in Notebook to make it more graphical and to be able to easily copy my files. So Brave Notebook and name of our instance. Okay, let's go to localhost 8888, and here we have our instance. So basically, when you create a new instance, what you need to do is to copy your files, fine-tune file, and that validation and data files here. I will not do it now because I have it already here. You can also copy requirements.txt file with a bunch of libraries you need for that. I written here. You'll have it all on GitHub. When copy it here, let's say you copied that, you can just pip install -r requirements.txt that way. And what we can do now is to run our fine tuning. Write python fine-tune.py and click enter. We can see first the weights and biases is loaded. After that, it's uploading our model to GPU. Now you can see that it started training, and it's going quite fast. 8, 9, 10, and so on. Iterations over 175. Every 10 step you can see it makes evaluation. And in meanwhile we can go to weights and biases page, and I will show you how you can use it to see your results. Go to your project, and here we have our run. Green is online, so our run is currently running. Basically, main chart we interested on is the evaluation loss. You can see how does that evaluation loss is going lower and lower with every step. And basically our task after the training will be find the lowest loss. So the lowest is loss is better for us, is the better performance of the model. And finally our training is finished and we can see our loss function here. For some first, let's say 70 steps, it was getting lower and lower, and after that it stuck for a little bit. After that it started to go worse, so probably if we continue the training, that loss will go up again. So basically it's not good idea to overtrain the model, and it's better just to find the spot where the model is trained enough but not too much. So as we can see, that new folder with our generation is appeared here, and we have few checkpoints. As you remember, we making checkpoint every 25 steps, as the 25 steps is one epoch in our case. We can use checkpoint number 75 or maybe 100 to inference with our model. Let's go now to the inference script. I'll show you how it's looking. First of all, we specify our model name, and here let's provide our Zephyr and checkpoint number 75. After that, we need to again apply quantization, same way as we did it during fine-tuning. Obviously, we provide here our base model ID, applying fine-tuning, and also applying our training weights. Here is already my model with our fine-tuned changes. After that, we add in here tokenizer, and everything looking the same except of the lack of the add end of string token line here, as we had it in, as you remember, in fine-tune tokenizer. See there, we had here at OS token, but in the inference we have no end of string token, only beginning of string. Why? Basically, the reason for it is that we asking our model to end the string. When we training our model, we give it some data like begin of string token, input data, some separator, output data, and end of string token. But when we doing inference, we doing only begin of string token, input data, maybe some separator also, but a rest of the string our model needs to grasp, needs to fulfill. And that's the point. That's why we don't want to add here any end of string token, because rest of the string with the end of string token our model will fulfill for itself. And here our generate response function that receiving prompt on its input, and model obviously tokenizes our received prompt, passes it to GPU, and generates our response. So we have provided our model inputs from GPU, we provided our max new tokens number, 200 in that case is totally enough. Do sample, not really sure what it's doing, can't answer you, and providing that IDs for end of string and path tokens. And after our response is generated, it's generated in the form of numbers, and that numbers we need to, after that, decode to the human understandable words. That's why we decoding it here, and after that returning our decoded output. You can experiment with that function also. You can add some print statements here, here, to see how does look that generated indexes, how does look decoded output, and so on. And after that, we again making our chat prompt template, to after that apply chat prompt template and make it automatically without thinking about which way of choosing separators is good for that model. That way is kind of universal. And in our chat prompt template, we only providing one message, the user message with input data, and nothing more. The rest of that model need to fulfill. Okay, so that there we applying that template, providing template, asking it not tokenize it now, but we'll tokenize it later inside of the function. Because when I trying to tokenize it at once, it's also possible, but there's some different format and there's some problems with formats mismatch and so on. So it's better to tokenize it later, but it's also possible to tokenize it in that step. And also generation prompt parameter set here to true means that after our input we provide a separator before the response. So it means normally our prompt will something like that. I'm user, and here is input, and without that it will be all, and that string our model we need to continue. But with that separator we just add in the also assistant statement, and just after that model we need to continue the string. So both of the ways will work, but that way is better because we're providing more data for our model. Okay, so we generated our response and basically printing that response. That's all. How to include that response into our Mars rover, into our Raspberry Pi, we'll talk in the next video. In that video I will just want to show you how to fine-tune our model. Let's copy our interference file here and let's try to run our model. Let's see how it will perform. Our model is uploaded and let's wait for generation. Okay, after a while I found that for checkpoint number 100 it works much better. 75 was probably not enough trained, and we can see our response here. We have some separators added, the beginning of string, token, user separator, input data, and after the separator of assistant. By the way, in input data we can see that we have some dust clouds on the front, at right we have a crater, but at the left and the rear we have the clear space. Also our container is empty. So let's read what our model is returned. Well, the reasoning is the container is empty, so exploration is the priority. Dust clouds at front and crater at right make those directions difficult or impossible to travel. Clear spaces at left and rear lead to options for movement. Move left, and we go on left. And we can see that reasoning and decision is very good, it is what we want, but there is a problem. You can see that for some reason our model didn't stop here, but started to generate new and new and new JSON until his context length is ended. Strange, yes? So basically that problem I mentioned only with the Zephyr model. With Mistral or Delphin there no such problem like that. And what we can do is that. So basically probably if we will provide here more training data, I think it maybe could be improved, but in our case we'll do another thing. Really brutal and not really clear, but it will work. So basically what I want to do is I want to cut out our response on that bracket. On the just first closing bracket our model mentioned, our response will be cut out and all. To do this, let's first of all find our number of token for that closing curly bracket. To do that, let's just encode our text with that bracket. And you can see our response. Basically, 2 at the end is our end of string token, but that number is the token of the curly bracket and also that quota. For 2 of the signs, it's like one common token. So just copy that number and pasting it here for the variable closing curly bracket token number. And next, in our generate response function, instead of end of string token ID, we'll place that curly bracket as end of string token. So think about it. We just provided instead of true end of string token ID, that curly bracket token ID. So when our generator will find that curly bracket, it will just finish the generation. As I said, it is not good practice and I don't really recommend to do so. Much better, I think, to train your model properly. But, well, in some cases like that, it will just work. Let's run it now. Container is empty, so priority is to collect minerals. Dust cloud at front make it risky to drive. Crater on right is also risky to be navigated. Clear spaces on the left and rear are the least risky options, so proceed left to gather minerals. Direction left. Again, it chooses direction a good way and cut off its response on the closing curly bracket. So as you can see, our fine-tuned model works and works totally only with input data without any instruction provided and knows which format it should generate the response. And in next video I will show you how to implement that fine-tuned model on the Raspberry Pi inside our Mars rover. And in that video we successfully fine-tuned our model. I hope it was understandable. If not, as I said, please write your questions. I'm satisfied with the results. They really better than we were in the previous video when we used not fine-tuned version of Zephyr. In today's video we only fine-tuned the model, but in next video I will show you how to make interference of that model on your Raspberry Pi or other microcomputer. Stay tuned and see you next time. Bye.